Welcome back, Year 12s, to another video on circular functions. In this video, we're going to look at one of the more challenging parts of this chapter, which is solving trigonometric equations. This pops up very often on exam 1, and so you'll need to be able to do the exercises in this video without notes and without a calculator. So let's get right into it. I'd like to begin by considering a very simple equation, sine of x equals a half. And when you start doing these questions, you'll be given a domain to consider, such as 0 to 2 pi or 0 to 4 pi. In this video, I'm actually not going to worry about domain restrictions. I'm going to consider all possible solutions for x over the real number, and I will leave it up to you as the student to find the values that fit within your domain. So let's think for a moment. Where does the half come from when working with sine? Well, if we draw our trusty right-angled triangle with side lengths 2, 1, and root 3, pi on 3, and pi on 6, we can recall that sine of pi on 3 is a half. But we also have a sense, working with the unit circle, that there are multiple solutions. So for example, if I know that sine of pi on 3 gives me a half, there is another solution obtained from pi minus pi on 3. So already we have some sense that there are two solutions. We know that sine of pi on 3 is a half, and we also know that sine of pi minus pi on 3 equals a half, or sine of 2 pi on 3 is a half. Okay, so we've got two solutions. We've got pi on 3 and we've got 2 pi on 3, and now we need a way to capture the fact that every time we add 2 pi to the angle, it's still a solution. So we actually have two families of solutions. The first family is pi on 3 plus 2n pi, where n is an integer, which I'm going to denote by the letter capital Z. So if you've forgotten, I'll just write this for you. These are the integers, which are the positive and negative whole numbers. Okay, so I can go forwards by 2 pi, I can go backwards by 2 pi, and I can cycle around as many times as I like. All right, so that's one family of solutions. And then the other family of solutions is 2 pi on 3 plus 2n pi. This is my set of all possible solutions. Okay? By using this parameter n, where n is an integer, I've captured every single possible solution. I don't need to write pi on 3, 7 pi on 3, 13 pi on 3, ... That's all captured in this first solution set. And then the other family is 2 pi on 3, 8 pi on 3, 14 pi on 3, and etc. So if you're given a question where you need to restrict the domain, all you need to do is pick suitable values of n and repeat until you've gone outside your domain, and then you start to exclude those solutions. Okay, let's do another one. This time we're going to consider cosine of 3x equals a half. So again, I'll draw my trusty triangle. You'll memorize this eventually, simply by the fact that you've done it so many times. So, I've just realized I've done this wrong, because sine of pi on 6 is a half. Apologies. Even when you draw the triangle, you can get it wrong. All right, so watch as I fix this. So my solutions are actually pi on 6 and 5 pi on 6. And by the power of technology, it looks like nothing happened. But you know because you've seen the video. All right, so yeah, I thought something was wrong because I changed it to half for cosine and I had pi on 3. Okay, so pi on 6 and 5 pi on 6. The only thing that's different after that point is you add 2n pi. Okay, apologies for the error. But notice how we picked it up. And that's a skill that we need as method students as well. Okay, back to cosine. So we are seeing that we've got a solution. Cosine of pi on 3 is a half. And we know that cosine is positive in the fourth quadrant. So this is 2 pi minus pi on 3. So cosine of 2 pi minus pi on 3 is a half, or cosine of 5 pi on 3 is a half. And this suggests that there are 4 possible solutions. Two families of solutions. The first family is going to be pi on 3 plus 2n pi. And the second family is going to be 5 pi on 3 plus 2n pi, where n is an integer. Now, some people would actually choose to write something else here. You could also write negative pi on 3 plus 2n pi. And the reason for that is to get from 5 pi on 3 to negative pi on 3, all I need to do is go backwards by 2 pi. Now, I've just noticed another error. This is 3x, so this here should be 3x as well. Okay, so just make note of that. And before I spotted that error, what was I saying? 5 pi on 3 is fine. Negative pi on 3 is fine because all I've done is I've gone backwards by 2 pi. Okay, so I'll just write that note here for you. So I'll say this is just going back. This is just taking away another 2 pi. Okay, now we can divide both families of solutions by 3 to get x. So divide pi on 3 by 3, I get pi on 9. And now 2n pi becomes 2n pi on 3. And similarly, 5 pi on 3 becomes 5 pi on 9, and 2n pi becomes 2n pi on 3. Now, one question that some students will have at this point is, do I need to combine the two? Do I need to combine something like this into one fraction? And the answer is, you don't have to, but you need to know how to in case you are given something like, say, a multiple choice question in exam 2, where they give you a bunch of options. Your CAS calculator can also generate these solutions for you as well. Okay, I've got a few more examples, but I want to take a little bit of time now to discuss why you might get negative pi on 3 coming out of your calculator instead of 5 pi on 3. And this issue is not treated in depth in maths methods because it overlaps a little bit with specialist maths. And the short answer is your calculator will use something called the inverse cosine, which is the inverse function of cosine. But if you think of cosine, it's a many-to-one function. And so in order to define an inverse, we have to restrict the domain. So I will show you what those functions look like, just to give you some background knowledge, but you won't be tested on it explicitly. All right, so let me remind you what sine, cosine, and tan look like. And I know we haven't done a tan equation. There's one coming soon. Now, I'm going to just draw parts of the graph of sine and cosine so that they are one-to-one restrictions. So the graph of sine goes to 0, 0, pi on 2, 1, and negative pi on 2, negative 1. And I claim that this captures the entire range of values from negative 1 to 1, and it's a restriction that defines a one-to-one function. Now, cosine is similar, except this time we don't start at negative pi on 2, we actually start at 0. And the reason why should be obvious. If we did it like this would now be a many-to-one function, which is not what we want. So pi on 2, 0, and 0, 1. Tan is interesting because it has asymptotes. Tan is already a one-to-one function, provided that we just consider it between the first two asymptotes. Okay, it's a point of inflection which is non-stationary at the origin, so it shouldn't be flat. And to give some indication of scale, I'll say it passes through pi on 4 and 1. We'll sketch tan graphs a bit later in the chapter. Okay, so these are what I will call the sine, cosine, and tangent functions over the domains from which we define the inverses: inverse sine, inverse cosine, and inverse tan. You'll notice that the domains for sine and cosine are different, and that's simply a matter of choice. We could have chosen something else, but I think as you're looking at this, it should be clear that these are somehow the simplest possible choices we could have made. If we made any other choice, we would have had to have gone further away from the origin, which doesn't really make sense. So once we do the inversion, all the x and y coordinates will swap, and the curvature or the concavity of the graph is going to swap. So you'll notice that the graph looks like this. So when I sketch the inverse, it's actually going to look like that when I reflect about the line y equals x. Sine has stationary points at neg pi on 2 and pi on 2, so the tangents should be vertical at the endpoints. So now inverse sine has endpoints negative 1 and 1, passes through 0. Inverse cosine will pass through the points 1, 0, and negative 1 pi, and 0 pi on 2. And tan will look like this. So now the asymptotes will be y rather than x. So neg pi on 2 and pi on 2 will still have a non-stationary point of inflection at 0, 0. And the points pi on 4, 1 maps to 1, pi on 4. Now, do you need to know these graphs? No. However, you do need to know the following facts, which I will state on the next page separately. Okay, so here's what I want you to know. I need you to know that when the CAS calculator returns a value for inverse sine and inverse cosine, and inverse tan, you need to think of these as functions with a domain and range. So for inverse sine, the domain is -1 to 1 because sine can only take on values between -1 and 1. Same with cosine. However, arctan or inverse tan, I can take the inverse tan of any number. Now the range for inverse tan is -pi/2 to pi/2 with the endpoints excluded because tan is undefined at plus or minus pi/2. Now I'll sketch the graphs again for you. So inverse sine looks like this. So it was 1 pi/2, -1 neg pi/2. Inverse cosine looks like this. So 1, 0, and -1 pi, 0 pi/2, 0, 0. So you can see that the domain of inverse cosine is going to be, the range is 0 to pi, whereas the range for inverse sine is neg pi/2 to pi/2. So please just note this carefully. When your CAS calculator gives you these values, they might not be what you expect them to be if you're not aware of the issues surrounding inverse sine and inverse cosine. Okay, it's a technical matter, but it's something that you need to know if you're aiming for very high marks in this subject, which is why I'm covering it. And now that I have suitably defined inverse sine, inverse cosine, and inverse tan, I'm now in a position to write general solutions for sine, cos, and tan equals some number alpha, where in the first instance, alpha is between -1 and 1 for cosine and sine, and of course for tan, alpha could be any number. So what are the general solutions? Well, for sine, I'll just assume without loss of generality that alpha is in the first quadrant. It doesn't have to be, but if it's not in the first quadrant, it's still going to work because of the symmetry properties of the unit circle. So essentially what we want to do is take the inverse sine of alpha. That will give me one solution, which is either going to be in the first quadrant or the fourth quadrant, and then plus 2n pi. The second solution is going to be pi minus the inverse sine of alpha plus 2n pi. So you can think of this as your quadrant 1 solution, and you can think of this as your quadrant 2 solution. But the assumption here is that alpha is in the first quadrant. Now, if alpha was in the fourth quadrant, if I did pi minus some angle, which was in the fourth quadrant, I would actually be adding. Because if alpha is less than 0, then inverse sine of alpha is less than 0. So pi minus inverse sine of alpha is greater than pi, placing me back in the third quadrant, which gives me a negative solution. So it still works. Okay, so I'll leave this as quadrant 1 and quadrant 2. But in red here, I'm assuming that alpha is positive. Okay. So these are actually the quadrant labels, so I'll put them in a different color as well. I'll just do it in a different color. Here we go. All right, so one moment, please. Okay, so this is quadrant 1. This is quadrant 2, and if alpha is positive. Same thing for cosine, so we'll do something similar. So we know that cosine is positive in the first quadrant and the fourth quadrant. So the first solution will be inverse cosine of alpha plus 2n pi. And the second solution, we could write this in several ways. We could write 2 pi minus inverse cosine of alpha plus 2n pi. Or we could actually just write negative inverse cosine of alpha. Because all I need to do is take away 2 pi to get from this solution to this solution. So this one is actually simpler. So we're going to go with this one. This is quadrant 1, and this is quadrant 4. Provided that alpha is positive. And sometimes we write this even more simply as follows. We write this as x equals plus or minus inverse cosine of alpha plus 2n pi. This combines both families into one single equation. There's another way to do this for inverse sine as well. So I might run out of space here, but that's okay. It's kind of slick. So essentially what you want to do is you're going to say inverse sine of alpha plus negative 1 to the power of n pi. I'm just checking that this is correct. So if n equals 0, that works. If n equals 1, sorry, I think I've remembered this wrong. Great. I think that's correct now. So you start at 0. If n equals 0, I go forwards, and So what we want to do, so we're going to add n pi. If n is positive, we will subtract inverse sine of alpha. If n is even, we will add it. So the way we account for this is with this factor minus 1 to the power of n. And instead of adding 2n pi, I add n pi. So it's like if n is positive, you subtract inverse sine. If n is even, you add it. Apologies for that. Okay, last one. This has taken up more room than I was expecting, so I'll just move everything up. Okay, so tan is positive in the first quadrant and the third quadrant. So the way that we will take care of this is to say x is the inverse tan of alpha plus 2n pi. In a moment, I'll collapse this, or x equals pi plus inverse tan of alpha plus 2n pi. And this, of course, is the first quadrant solution, and this is the third quadrant solution, provided that alpha is positive. But we can actually write this more concisely, just like we did for the sine solution, and that is as follows. So the general solution for tan x equals alpha is x equals inverse tan of alpha plus n pi. So instead of 2n pi, we'll just need to add any multiple of pi we like and add on inverse tan of alpha. Now, I'll leave it to you as an exercise to check that these general solutions will work for cosine and tan when alpha is negative. It's pretty straightforward. It should take you a couple of minutes to do. Now, I do apologize for the hiccups with this slide and with the first slide. We've got a couple more examples and then we're done with this video. And if this was heavy, it's because I've kind of covered the general solution exercise as well at the same time as doing this exercise, because I think they go together. Okay. The last thing I want to do is two examples where the equations are non-routine. So let's start with cosine of x equals root 3 sine of x. This looks strange because it looks like normally you're used to seeing just one trig function. It's not really obvious what we would do here, provided you've forgotten something. If you remember the trick, then this is a very easy question to do. First thing I'm noticing is that root 3 is here. Root 3 is special. Root 3 is closely related to the exact values for sine, cos, and tan. The other thing I'm noticing is that sine and cosine are both present in this equation. And there's a definition for tan, which involves sine and cosine, which is as follows. So if I divide both sides by cosine of x, as follows, I will transform this equation to a tan equation. Now here, I have to make the assumption that cosine of x is not 0. So it doesn't matter too much here, but in general, when you divide an equation, you need to check that your denominator equals 0 also contributes a solution to the equation as well. So we'll come back and check this at the end. So I'll say, provided cosine of x is not 0. So now we get 1 equals root 3 tan of x, or tan of x equals 1 on root 3. And now I can write down my general solution, which is x equals the inverse tan of 1 on root 3 plus n pi. And because I know my right-angled triangle, and hopefully I'll get this right this time, pi on 3 is here, pi on 6 is here, tan of pi on 6 is 1 on root 3. So x is pi on 6 plus n pi, where n is an integer. You need to state this, you need to say that n is an integer, and I should have done this on the previous slide as well, so I'll do that. So here, I'll just say, assume n is an integer. Please make sure you write this when you write a general solution, otherwise you will not gain the mark, I'm pretty sure. Okay, now let's check. If cosine of x equals 0, then sine of x is plus or minus 1. So cosine of x equals 0 does not contribute any additional solutions. And thus, our last line there, x equals pi on 6 plus n pi, where n is an integer, accounts for the full set of solutions for this equation. Okay, one last example. This looks like a mess, doesn't it? Sine squared, what are we supposed to do? Well, the trick is to use a quadratic substitution. You're used to doing this for logs and exponentials. We can also do this with trigonometric equations as well. So let u equal sine of x. The equation now becomes 2u squared plus 3u minus 2. At this point, we have a quadratic equation, which we can solve either through factorization, completing the square, or the quadratic formula. Since 2 is a small prime number, I'll start by checking whether we can factorize it by inspection. So now I'm looking for two numbers to go on the right of both brackets, which multiply to -2. And the obvious choice is to make 4 from 2 times 2 minus 1, which tells me that u equals either a half or u equals -2. We will reject u equals -2 since sine of x is between -1 and 1. That is, there are no values of sine of x, which gives me -2. So therefore, I only need to consider the equation sine of x equals a half. And that means I'm going to have a solution in the first quadrant and a solution in the second quadrant. The first solution is going to be, well, let's use the general solution formula. How about that? So it'll be -1 to the power of n, inverse sine of a half, plus n pi, where n is an integer. And I guess I'll draw the triangle again. 1 root 3 and 2. Sine of pi on 6 gives me a half, and I've got it right this time. So it's -1 to the power of n, pi on 6, plus n pi. The important parts of the solution to this equation were here, here, and don't forget, you need to clearly define what your parameter means. Please do not say n is a natural number, because it's not wrong, but it doesn't capture all of the solutions. N is an integer, because I'm allowed to go forwards or backwards by multiples of 2 pi. Please also do not say that n is a real number, because that would mean x is a real number. No, n is an integer. You are counting forwards or backwards by integer multiples of 2 pi. Okay, this was a heavy lesson, but if I were to break this down into a very brief summary, here's what I would say. I think these are your steps. So first, you've got to set up a trigonometric equation. Then you've got to identify the quadrants contributing to your solution. If you want, write down the general solution. And at the end, what you may need to do is take into account domain restrictions. Now, if you're fast, you may not need to do this. Once you're experienced. But my suggestion is you do write down the general solution because you're expected to know it, and yes, it has come up in exam 1. So I kid you not, these results on this page, you could be asked for these in exam 1. You wouldn't be asked for inverse sine, inverse cosine, inverse tan. Alpha would be a number that gives you an exact value. Okay, I think if you find this video unclear, I'll tidy it up in class tomorrow, and I may just record this video again for clarity's sake. Thanks. See you tomorrow.